show that 2 plus 3i over 5 plus i is equal to k times 1 plus i, where k is constant to be determined. Right, so let's, well, I was about to say rationalize the denominator. So 2 plus 3i, but it's the same idea. We times by the conjugate, complex conjugate of the denominator, so 5 minus I over 5 minus I, which then gives me, okay, these are double brackets, so I'm going to get 10 minus 2i plus 15i. Actually, I don't want to rush it. Minus 2i plus 15i, and then minus 3i squared, which becomes plus 3, all over 25 minus 5i plus 5i. That's precisely why we're doing this, because we get rid of the imaginary parts, minus I squared, which becomes plus 1. That's 13 plus 13i over 26, which then simplifies to 1 plus I over 2. Okay, we're nearly there. A half times 1 plus I. There we go. I might write down k is a half. I've determined it. It's implied in my answer, but there we go. Okay, and then given that n is a positive integer, and this to the power of n is a real number, use our answer to a to write down the smallest possible value of n. Okay, so when I did this, I just thought I'm just gonna square. I mean, there's different ways to do it. In fact, one really quick way is to say, okay, 1 plus I is over here, and this would be a 45-degree angle. When I square the complex number, I'm gonna basically, whatever the argument is, I'm just gonna be doubling it because you add the arguments together. So it's gonna end up along the imaginary axis when I square it. If I then times it by the same thing again, I'm gonna end up over here. Times by it again, the fourth time, I'm gonna end up along the real axis. So without actually doing a calculation, you can write down that n is gonna be 4. Okay, if you don't see that, then let's just multiply it. 1 plus I squared is 1 plus I times 1 plus I. Okay, so actually, let me write it like that. That will give me 1. Then it'll be plus I squared. So that's actually minus 1 plus 2I. So I get 2I. Then I can see that if I do 1 plus I to the power of 4, then I'm going to get minus 4, which is precisely kind of what I was talking about over here. So again, we get that n is 4. Then complex number z plus a plus bi is given, where a and b are real constants. We're then given that the modulus of z to the 10 is 59,049, and the argument of z to the 10 is minus pi over 3. Determine the value of a and the value of b. So when you have a complex number in modulus argument form, if you times them together, you just times your moduluses together. So if I want to find out what the modulus of z is, all I got to do is undo this and take the 10th root of 59049. And you can guarantee this is going to be a nice number. In fact, it ends up being 3. And something goes on with the argument when you multiply complex numbers together. You actually add the arguments together. So essentially, we've taken z, we've times it by itself 10 times, we've added its argument together 10 times, which means to get the argument of z, I need to divide by 10. It's going to be minus 5 pi over 30, which actually ends up being minus pi over 6. So then, to work out z, I can write it as the modulus of z multiplied by cos theta, where theta is the argument. Just a bit easier to write theta, plus I sine theta. So that's going to be 3 times cos minus pi over 6 plus I sine minus pi over 6, which is equal to 3 root 3 over 2. minus 3 over 2i. So I have stated a couple of facts here I've used without any proof. I'm just going to write them down again. So if I have the modulus of z1, z2 is equal to the modulus of z1 times the modulus of z2. Again, no proof there, but that is what I've used to undo it and get back to the modulus of z. And then in this situation, the argument of z1, z2 becomes the argument of z1 plus the argument of z2. You can use addition formally to prove that one. So these are the two to be aware of that we've used. Hopefully you're happy with that. Brilliant.